So today we will learn a new chapter that is called PMMC instrument. Okay, I think my screen is visible now. So first of all, this PMMC instrument is a part of the moving coil instrument, and today we will discuss about its construction and working principle and its advantages and disadvantages along with its applications. Okay, so I think my screen is visible, so let me. So coming to the construction of this PMMC instrument, here are the major parts of this PMMC instrument. Here are the permanent magnets, okay, and a rectangular core, and which is made up of mostly uh, aluminum or any kind of a non-magnetic substance. Okay, and apart from that, there are several coils formed with this rectangular core, and inside this core, a spindle has been attached. Okay, and on that spindle, a pointer is mounted along with this balancing weight. Okay, and on that spindle, also there are two spring or one spring also added for control mechanism. And here the balance weight is mounted on this pointer uh, for damping mechanism. Okay, so so this is the arrangement of this PMC instrument. Okay, so these are the two permanent magnets. So these magnets are basically kind of a horseshoe magnet. Okay, so between these two poles, the core is sandwiched between them. Okay, next back to its working principle. So the basic thing is here is a core has been mounted, but whenever a supply given to this whenever a supply given to this core, that means for this core, some coils are some coils are wounded. Okay, and this coils has two terminals. Okay, so one is the starting and one is the ending terminal. So uh, between that terminals, we are providing a supply, an electric supply. Okay, so that a current will pass through this closed loop. Okay, the current will pass through this closed loop, and prior to that there is already a magnetic field present uh, around this core. Okay, so because already permanent magnets are established here, so here is the south pole, here is the north pole. Okay, and the magnetic lines of force already passing through this area, that means from north to south. So in between that north pole and south pole, this core has been sandwiched with some coils. Okay, so whenever the as we know the law, according to the Lorentz force, so or and you can say Fleming's right hand rule. Okay, so whenever a current carrying conductor placed in this magnetic field, it will experience some force. So we can say that, so this is kind of a rectangular force, the magnetic lines of force passing through this from north to south. So the effective part of this coils, so the effective part of these coils are only this vertical section, not this horizontal sections. So the only the magnetic lines of force will cut through this vertical section of this course. So what happen whenever a current carrying conductor placed in this magnetic field, so it will deflect, that means it will experience some force. So the left side vertical coil uh, might move upward or downward. Similarly, from the right side vertical coil might be deflect either upward or downward. So in this way, the coil will rotate, and the pointer will the pointer starts to moving, or it's actually a it shows a value from this calibrated scale. Okay, So the scales here, actually I forgot to mention this. The here we can here we can calibrate the scale as per our need. Okay. So as of now, for this PMC instrument, we are using as a galvanometer. Okay. So the main working principle is nothing but if we provide an electric supply to this wounded coil, then this pointer will start to move, and it will provide some value as per our need, whatever we are trying to measure. Okay. So for now, if we are using as a galvanometer, it will only deflect either either of any side, it will deflect. Okay. And coming back to this control mechanism, so if a pointer, if this pointer has been moved to any particular direction. Okay, let's suppose we are measuring something. Let's suppose we are measuring, we are using PMC as an ammeter. So if the pointer starts to move from 0 to a particular value, so it should be in a steady position. Okay, it should be in a steady position. Then if it will not steady, it will keep vibrating. So the accurate value we cannot achieve. Okay. So for this only we are using this damping mechanism, this balancing weight mechanism. So as we studied in our damping torque mechanism, we are using this balancing weight. So it will provide a damping mechanism so that it won't be vibrate. So it will stay as steady at a particular value. Okay. Then the basic thing is that the other control mechanism. So if a pointer starts from 0 to a particular value, so it should return back to 0 when the supply has been disconnected. Otherwise it will stay here. So the springs are mounted on this spindle in this way. We can say here, if the spring is rotating in clockwise direction, the spring might be expand, or the spring might be compressed. So let's take we are mounted the spring in that way. If the spindle rotate clockwise, the spring will compress. Okay. So what will happen? This pointer will deflect from 0 to a particular value, and due to this balancing weight mechanism, it will stay as steady. Okay. It is defining a particular value here. So what will happen? So this pointer, then whenever we disconnect the supply, this pointer should come back to 0. So how it will come back? Whenever the spindle is rotating, the spring is storing its actually kinetic energy. Okay. So now it's actually storing its now it's storing its potential energy. And when the electric supply disconnects, the spring will convert its potential energy to kinetic energy, so that the spring force will bring back the pointer to its initial position. Okay. And there are a couple of bearing mechanism here. So the spindle will rotate very comfortably. Okay. And yeah, that much. Let's go to this torque derivation of this PMMC instrument. Okay. So as we know, we actually previously studied that the electromagnetic, you studied about this electromagnetic torque. Okay. So what is electromagnetic torque? That means that the same Lorentz force actually, whenever we are placing a circular rectangular coil in a particular magnetic field, its effective coils are it effective coils cutting the flux, and it will experience some force. So in this way, a rotating torque will generate. Okay. So its formula is nothing but T equal to force into applied current. Okay. So here TD we denoted as the deflecting torque. Okay. And what is about this force? The force formula is nothing but N, B, and A. Okay, so here we can neglect N also when we are using only one coil. So N is nothing but our number of turns of the coils. Okay, so and B is nothing but our flux density. Okay, so its unit is Weber per meter square. Okay, and A is the effective cross-sectional area of the coil. That means when I'm saying that a particular rectangular coil, which parts are effective, so that area we are only considering. So in that case, in this rectangular case, the mostly the vertical part of the coils are most effective. Okay, so and I is nothing but our applied current. So the deflecting torque produced by this PMMC instrument is nothing but TD equal to N, B, A, and I. Okay. Okay. Next we have to come to your controlling torque. Okay. So whenever a pointer starts from zero to its particular value. Just a second. Okay. I will go with this then. So whenever I said that a a rectangular coil, that means it's moved from zero to a particular value. So at that time the spring actually either compressing or expanding. Okay. So it actually it actually storing some forces, and that means potential energy. So after some couple of seconds, after when the instrument is disconnected, then it will release its potential energy in terms of kinetic energy. So how much the torque will generate? So the torque will generate uh, this much. The TC equal to K into theta. So what is the theta? So if we go back to this slide here, here we can see that here is the initial position and here is the final position. So whenever it pointer moving from 0 to a particular value, it moving from it moving it will moving with an angle from its point of reference. If we take this is a point of reference, so it will moving from a particular angle like 10 degree, 20 degree, 30 degree. So as per the supply, uh, it will move from its initial position to a particular value. Okay, so the TC is nothing equal to K into theta. So what is K? K is nothing but the spring constant. Okay, so we can term as in terms of Newton meter per degree or Newton meter per radian. So we can as we know, we can write the angle in terms of degree or radian as per our requirement. Okay, so for steady state condition, what is the steady state condition means here? So if a pointer is here and see, if we don't provide this control mechanism, that means the deflecting torque keep producing, and this pointer will rotate 360 degree, will continuously rotate 360 degree, which is valueless. So to overcome this, we have provided this control spring mechanism. So whenever the deflecting torque is same as your controlling torque, then the pointer will is situated at a particular position. It won't be revolved up to 360 degree. Okay. So when it will happen? It will happen when actually steady state condition, when the deflecting torque value equal to the its controlling torque, then the pointer will keep steady position. So when this happen, what will happen then? So the value of deflecting torque, as we know, that NBIA, that means F into I equal to K into theta. Okay, so F is a constant thing Okay, so we are providing, and we are varying the only current, like sometimes we are providing 5 ampere, sometimes we are providing 4 ampere, or sometimes we are providing multiple values of current. Okay, but the force which is produced inside that instrument, that is constant. Okay, and here the spring constant also constant. So we are taking a very we are taking the constant things into a particular side. Okay, so here theta equal to f by k into I, we can term as f by k a particular constant. Let's take it as a c. Okay, so theta equal to ci. So if we remove that constant, we can say that I is directly proportional to theta. That means how much current we are providing, it will deflect from 0 to its particular angle. Okay, so what is the deflection angle? Basically, when a pointer moves from its initial position to a particular value up to how much degree or how much radian. So the whenever we apply x amount of current, the pointer will deflect theta amount of theta up to theta degree deflection. Okay, so basically our PMC instrument is directly proportional to the applied current. Okay, and coming to its application, uh, we can use this PMC instrument as an galvanometer, as I just said, and we can use this PMC instrument as an ammeter also. Okay, so for this ammeter, we have to do some modification in this instrument. Okay, so what is the thing actually we are doing here? We are providing a parallel resistance or parallel shunt, we can say, in with this with our basic PMMC instrument. So why we are providing? Let's suppose the manufacturer made a PMMC instrument. Okay, so initially the PMMC instrument resistance is very high. Okay, and so they are generally measure very low amount of current, like we can say 50 milliampere, 100 milliampere. Okay, so to extend those range, okay, so we are providing a shunt resistance to this parallel with this PMC instrument. Okay, so whenever we are providing high amount of current, and uh, and okay, another thing that the shunt resistance is very much less than this meter resistance, PMC instrument resistance. Okay, so whenever we are providing a high amount of current, so the maximum current will flow through this shunt resistance, and the required amount of current which can be bear by this PMC instrument, that much amount of current flows through this instrument. Okay, so for this only we are providing a shunt. Okay, shunt resistor to use an to use PMC instrument as an ammeter. Okay, and coming back to PMC instrument as an voltmeter. So for voltmeter, every arrangement is same as per the previous arrangement. Here whatever the arrangement we have did, everything is same. Here we are just removing the shunt and attaching a single resistance with series with this PMC instrument. Okay, so previously we are attaching a shunt resistance with PMC instrument. Now we are adding a series resistance for to using like this voltmeter. So if we consider here, this is the series resistance we have added. This is the already meter resistance. So as we know, as per the Ohm's law, V equal to IR. So that whenever we give some supply, so how much the voltage will drop, it will deflect as much as the voltage drops occurring according to this total resistance. Here the total resistance is the series resistance plus meter resistance. Okay, and coming to the advantages, so this PMMC instrument has greater accuracy. Okay, so as we studied before, what is accuracy, what is precision. Okay, so thus the accuracy of this PMMC instrument is very much okay. Yeah, so yeah. Yeah, so PMC instrument has greater accuracy, and it always consume less power. Okay, and some of the other thing that here we are the Here, yeah, here whenever the one thing we have to remember that whenever we are adding some controlling mechanism for the spring, we are using a special material that is called manganese. Okay, so in this instrument, the manganese has been used, or if we use the PMC instrument as an ammeter or voltmeter, we are using the shunt or series resistance using the same metal, the manganese, because it's highly resistive and it's very less effective for any magnetic field. Okay, so it highly resistive, but it's more, we can say it's non magnetic. Okay, so that's why we are using that kind of metal for using suntan series. And yeah, and these are the advantages. So we can so here the torque derivation is that means current is directly proportional to the angle of deflection, so it will be easy to calibrate those scales also. Okay, and the damping mechanism and control mechanism is easy here. Okay, and it can be modified for ammeter and voltmeter as per our suitable needed. So if you want to measure 50 ampere, 100 ampere, 400 ampere, so that much a kind of resistance we have to add. Okay, so if you want to measure like the domestic supply voltage or higher voltage, so we can add according to our needed required series resistance also there. So what are the disadvantages is there? So the main disadvantage is in PMC instrument that it can only be used for the DC supply. It won't work for AC circuit. So for AC circuit, we have to use a rectifier for this instrument. Okay. And another disadvantage is here the coils are moving instrument, the coils are moving here. Okay, so for this moving coil mechanism, for this moving coil mechanism, the cost will be bit much high. Okay, and and in this PMMC instrument, if we use this instrument in a particular field where the external magnetic field is very much high as compared to this internal magnetic field, so there is a chances of very much error we can get. Okay, so for this external magnetism, for external effect of magnetism, we are providing a magnetic shield here. Okay, yeah, that much about this PMMC instrument. I hope you guys understand. Is there any question? Then you can ask. Thank you.